Okay, this is a radiological survey meter. Most of us know it as a Geiger counter. It has a probe, a bit of electronics in here, a couple of batteries. It is a device, as many of you know, it's used to give an account of how much radiation is present, what is the dose rate. Now, this meter, it's an analog meter, old school, is calibrated in counts per minute and millirems per hour. We're only going to be dealing with counts per minute here, and we'll get to why that is later. But this particular meter did not come with a internal device to make clicking noises. We're all familiar with a Geiger counter, tick, 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 tick. It does have a port for a set of headphones. I did add a piezoelectric speaker inside just to have it make clicks. Now it's kind of difficult to hear them with the box on, so I'm going to take the box off. And you can see there's the speaker. It's a little piezoelectric horn wired in. Okay, I'll turn this thing on. Yeah, you can hear it clicking a little bit. Background radiation. Here's the business end of the probe. This is they call this a pancake probe. You might get an idea why. But anything under here that emits radiation up to this, whether it's X-rays, gamma rays, beta or alpha, will get into that probe. So I have a box of sources here, radioactive, some of many. These are pretty low level stuff, but nevertheless, even in this box, they will react. The distance here, about 6 inches. So what's in this box? Well, oh, look at that. How do you do it hotter? First, my lowest level sources in that collection. A couple of marbles. These are glass marbles, but they contain traces of uranium, which is interesting. It makes them this odd light green color. It also, when exposed to long wave ultraviolet light, black light, they fluoresce brilliantly. It's truly amazing, really cool. But they are a little bit radioactive. Not a whole lot above background. Yep. Next source is this one. This was removed, or I should say liberated, from a modern smoke detector. It is americium. It's pretty low dose. As you can hear, I mean, that's not much above background. Even if you have the distance, roughly, a quarter it. Oh, but boy, you get this thing close. Oh, seems pretty close there, doesn't it? But watch this. for you to look up why that is. I know why. We're going to have another source here. And let's see if I can get... There we go. This seems pretty quiet too. This is also from a smoke detector, but a much older one. Probably made in the very early 70s, maybe late 60s. And it has a shield on it right now. Take the shield off. Oops. A little bit hot. This is radium-226. 0.05 microcurie of it. And it's, as you can see, it's a little hot. And you can see the needle drifting up. This is on times 100. Interesting, the cup this is mounted in does a pretty doggone good job of shielding. Oh boy. You get that business then facing the probe. And the shield. It does a pretty good job. But this is not something I'd want to carry around in my shirt pocket facing me. This next sample is a lump of uranium ore. Nothing special about it. Looks like a rock. Reddish looking. But it's got some spark. Okay, I'll put it down here. It's a little bit, maybe 7" away from the probe. And you can hear it's counting them. Remove this. Background. And of course, if you draw it closer, heats up pretty good. So we'll put that back in here. Okay. Typical Geiger counter. Nothing special. These things are a dime a dozen. All the probes cost a little bit of coin to get a good one. I'm going to go ahead and turn this off. Now I'm going to connect this probe to the instrument below, which you can't see right now, which is another sort of counter. It doesn't just issue clicks or give a readout on an analog scale like this one does. I'm going to leave this here just because it's a handy support for the probe. What I'm interested in, what I really want to show is this other instrument. It is a counter. It uses vacuum tubes to do the counting. Now I say vacuum tubes, they have some neon in them, which serves a number of purposes. It allows the counting, and it also displays the count of each tube. It avoids a whole lot of circuitry. The circuitry in this box is there's very little. It's solid state, and it's mostly power supply and some signal shaping that takes place. And basically what this does, it supplies the power to the probe just like this does, which in this case is about 900 volts, and the pulses that come from the the probe, rather than issuing forth as clicks and a reading on the analog scale, are actually counted on tubes, vacuum tubes. Let me lower the camera. There it is. So these are the vacuum tubes. There are 5, obviously. They're called Decatrons. They are counters. They also are displays, both in the same package. Each one of these can count to 10. And when this one counts up to 10 and rolls over, in other words, goes past 0, it sends a pulse to the next one, and he rolls around. There are no actual moving parts in these things. It's all just gases at work, in this case neon, that allow these things to count and display simultaneously. So, power them up. Now, it's hard to see, but around these are numbers. Probably see them as dots. It's 1, 2, 0 at the top, 1, 2, 3, 4, and all the way around to 9. Each one of these. When that light passes or reaches 0 on this one, it will trigger this one to advance by 1. Same thing. When this one goes to 0 again, this one will advance by 1, and on like that. So this counter can count to 99999, 99,999, or if it rolls over to zeros, well, 100,000. And I guess somebody watching would have to be careful of that. But if you're using a Geiger tube with a radioactive source, and these things roll over past 100,000 in a minute, you need to leave, because there's too much radiation. I've read this box was primarily used for educational purposes, demonstrations, that kind of thing, although it's pretty useful. It's called the Nucleus Model K. Interesting that it was made in Oak Ridge, Tennessee. Some of you may understand the significance of Oak Ridge, Tennessee. So this part is the counter. This part is the power supply for the tube. And right now the tube voltage is set to 0, so it's not going to receive any pulses from it right now. It won't do so until it gets up above 800 volts. The counter is, when you turn it on, set to some random number, which can be reset. Now these all read 0. It has an interesting feature. It has a test mode, and you set it to test and count. And what this does is it puts a 60 hertz, meaning 60 pulses per second, into this tube, similar to if this was putting 60 pulses per second into this tube, and it will cause it to count, and that count will roll over into this one, and this one will roll over into this one, and it's a kind of nifty way of calibrating the thing. It has an internal timer for 1 minute. It's an analog timer. It's an RC network. It's kind of dependent on temperature, humidity, pressure, and what time of day it is, but it does a pretty good job. So with 60 pulses coming in here, divided by 10, divided by 10, divided by 10, divided by 10, in 1 minute should be ideally 3,600 pulses. Well, let's see what this reads out. Now, this I can make this begin counting in test mode. 60 hertz, 60 pulses per second coming in, and so here we go. You see, every time this passes 0, this one advances. Same thing with him. Watch this, when he gets to 0, he'll move. And this will go on. If this keeps spinning, he'll advance too. Now in 1 minute, at 60 cycles per second coming, or 60 pulses per second coming in, this is not going to move far enough to advance him. Ideally, it would be 3600. But the calibration of the analog, there it just stopped. The calibration of the analog timer that times 1 minute, it's a little, it drifts a bit because it's kind of primitive. But there we go, 3, 6, 6, 2. Not too far off. So the 1 minute timer in here, based on the 60 cycles per second coming from the house current, which is pretty darn close, that makes sense. So it's pretty close. Okay. So I'm going to reset everything and turn on the voltage to the probe. And I'll leave it on count. Turn it off test and reset that. And as nothing's happening, but as I turn up the voltage to a certain point, it begins counting. This 800 volts. That's what's on the probe right now. The probe's rated for 900, but you know, there's a little bit of a window at which it'll work. But the spec for that probe is 900 volts. So I'm going to go to 900 volts. And you can see it's already got 1, 10, 11 counts. Actually 25 counts now. So I'm going to turn it up, make it stop counting. I'm going to reset it. Now when I push this down, it's going to count for 1 minute. Give or take, whatever. And that'll give me the counts per minute, which can be, given the probe driven with the voltage it's specified for, can give me the dose rate in millirens per hour, or sieverts, whatever you like. So here's my source again. I'm going to open him up. In fact, let me see if I can get him a little closer. There we go. That should do it. And for 1 minute, we'll see what the counts are from this, primarily from this uranium ore sample. Okay, that 1 minute, it stopped counting. The counts are 4, 3, 5, 4. So 4,354 counts per minute. The probe this far away from this sample, and whatever else is in this box. Not horrible, but it's pretty repeatable. But the niftiest thing about this darn thing is this test mode. I can watch this all day. The spinners. These tubes, they don't last for long. Well, they don't last forever, I guess I should say. They do have their limitations, but they do work. Counter and display all in one tube, and it looks just like any other radio tube. If you saw it, I'm not going to take this apart to show it. But yeah, it's not not looking very sophisticated, and there's no moving parts at all in these things. It's all just gases and ionization happening on these pole pieces. Pretty nifty.